All right, so now we are ready to build the meta learning system. So, in this situation, what we are going to do is we are going to generalize the Harlow experiment. Instead of just two objects and then one reward, which you have to associate with a particular object, we are going to create multiple task sets where you have different pairs of objects, one of which is rewarded and another not. And these are presented sequentially, right? And so you have to figure out across all these tasks which objects are rewarded and which are not, but you don't see all the objects at the same time. That's critical. Otherwise, it's not continual learning. This task set is analogous to the MAML tutorial. And so we want one model that can perform well on all tasks. So here, meta learning is very interesting because first, we don't want to learn from scratch every time we are introduced to a new task. So want some sort of transfer, at least in terms of like, okay, there is one object that I have to choose. So this can be handled with meta learning, and that organisms, when they are made to do the Harlow task, monkeys or us, we do it very fast. So this quick adaptation and forward transfer. So you learn something from task one, you could transfer it to task two. This is the realm of meta learning. This is where meta learning excels. So this task is perfect for meta learning. So what we want to do is we want to build one model with our meta learning algorithm that can then see these tasks sequentially and not forget what happened in the past while being faster and faster with every task. We'll build the first model which can do this, and then of course you can build further iterations by yourself which can go into much more detail. So the reinforcement learning agent that we talked about is going to be the inner loop of this meta learning model, right? So because it has to learn new object reward pairs, it has to use reinforcement learning. So A to C is going to be part of the inner loop, right? So in the inner loop we have task specific weights that are going to be part of the actor network and the critique network, and these are added on top of these base weights, and then you update only these task specific weights like what we did with mammal. Now, what should the outer loop be, right? We could do something like what we did with mammal. So in mammal, if you remember, we took the base weights and then we had the task specific weights. So first we optimized the task specific weights, then we held the task specific weights constant, and then we updated the base weights, right? So we could do that, but there is an alternative which is much better, and we'll talk about that now. So now we're going to take a step back and like think about a bigger picture, right? So this inner loop, this model that we want, is going to be present and doing the task in its lifetime, right? But this meta learning thing could happen outside its lifetime. You could think about evolution as learning, so that you can instantiate a bunch of models and then they'll do reinforcement learning in their lifetime, but then across many individuals of a population you can see who performs well, and then you know breed them and build new individuals which can do it even better, right? So we're going to use evolution as a form of meta learning. So in evolution, as you know, we have random mutations followed by selection based on survival. And just by doing this, evolution ends up discovering solutions to specific problems. For example, Darwin's finches, you probably have heard about it, where he found on the Galapagos Islands, he found finches with different beaks, and that he realized that these different beaks are evolved depending on the food they need to survive. This can be considered a form of learning. I mean, the beak was not learned during the lifetime of the bird, but it's something that was instantiated into the bird because, as a species, that's important. That's the prior, something like the base weights in this case. This is known as the Baldwin effect, that learning to learn contributes to organism survival. So we have these beaks and all of that, right? Like those are static priors, right? You're giving some physical abilities to the creature, but on top of that, we have learning abilities. And in 1896, the psychologist Baldwin was that capacity to learn contributes also to the organism's survival, because then you can, given a new situation, you can immediately adapt. Right? Not over species level adaptation with mutations, but within a life. So organisms that adapt quickly will survive longer and reproduce more, and therefore organisms should evolve to be good learners. Evolving to learn is a form of meta learning. That's the framework we are going to operate in. So how do we do this? So the outer loop can basically be evolution in this case, but how do we implement this evolution? So now we are going to talk about evolutionary algorithms. So the way these genetic or evolutionary algorithms work is that you create a generation or a population of, let's say, agents or systems, and then you evaluate these individuals, right? And then you take the fit individuals and then you breed them. So what would that look like? For example, in this case, you have these shapes with different colors, right? And then you have some evaluation criteria on it. Could be like there is some judge which is looking at these shapes and saying yes, no, and that's the evaluation, let's say. And so you take these shapes, then you say, well, this shape really had a bad evaluation. Then you do the reproduction stage, which is basically you cross features of these individuals from this population. So what you did here is you took the red big circle and the small black circle and you crossed. So you had a small black circle with red, right? Now, then you can do mutations on top of this. This is the reproduction, then you do mutations. So the red circle can become a bit larger, right? Or the green oval can become a dark green oval, for example. Right? And now these will give you a new population, right? That's a new generation. And then you again evaluate them and keep going. So what will happen is with every iteration, you keep on creating fitter and fitter individuals, right? And so that's how you get really good individuals at the end of your evolutionary loop, which satisfies the evaluation criteria. So our biologically inspired meta-learning method might look like this. You initialize base weights for agents in a population. You take a lot of agents, not just one. And for each generation, across all the agents, we do this task-specific weight optimization using reinforcement learning over all the tasks sequentially, right? And then we select the best performing agents. So the best performing agents in this case would be agents which learn, let's say, fast, also high performance, and don't forget, for example, right? And then we take these agents, then we mix their base weights, multiple criteria, so you'll see particular methods in the tutorial. And then we apply some random mutation, just change the weights a bit, right? And then now that's the new population. And then you go again through the loop. And in doing so, your base weights will become better and better. Better in the sense that you're creating systems which can then do RL continually. So that's the magic which will happen once we finish training in this way. So they will become good at the Harlow task, also adapting quickly to new tasks and not forgetting. So explore the Baldwin effect in your model.